Hi, I'm Isaac.
And I'm Lydia, and today we're going to be talking about lifting weights. So here's our problem. The current world record for the strict bicep curl is 102 kilograms by C.T. Fletcher. What is the tension in the tendon connecting C.T.'s muscle to the bone while the dumbbell is held stationary in the horizontal position? And what is the force sustained by the elbow joint? So usually we would try to visualize this problem, but today we can see it in real life. So today we were lucky enough to bring in our friend Chris to demonstrate the bicep curl. Hey Chris, thanks for coming. So can you demonstrate just bring up to the horizontal position? Perfect. So right now Chris's arm is in equilibrium, which means that the torques from his bicep muscle are being balanced out by the torques from the weight of the dumbbell.
All right, so in the first part of this problem, we're going to figure out the tension in the tendon connecting C.T.'s muscle to the bone. So let's go ahead and use this as a representation of C.T.'s arm. So since we're dealing with torque, we're going to label both the force and the distance here. So over here, we're going to have the force downward from the dumbbell, which we'll also say is equal to mg. Okay. And we'll also label the distance from the pivot point over here as x of d. And going up, we have the force of the tendon, and we'll call that distance x sub t. All right, so torque again is equal to force times distance. And we know that this system over here is in equilibrium, which means that the sum of the torques is going to equal 0. So we can have the force and the distance of the tendon, and we can add the force and the distance of the dumbbell, and we can say that it's equal to 0, right?
I think we have a problem here because we can see from the diagram that these two torques are opposing each other, but here in this equation they're adding together. So we need to make them oppose each other, make this one have a minus sign.
Mm-hmm. So we're going to put a minus here because they're in opposite directions. So now we can go ahead and rearrange our equation in order to solve for the force generated by that tendon. So over here, we have the force and distance of the dumbbell over the distance of the tendon. And we can go ahead and plug everything in here. So we know that the dumbbell used by C.T. Fletcher was 102 kilograms. We multiply that by force of gravity. And here for the distance of the dumbbell to that pivot point is, in an average human, around 35 centimeters. So we'll say that it's 0.35 meters. And all of that will be over the distance of the tendon to that pivot point, which in an average human is about 4 centimeters. So we'll say that it's 0.04. When we solve all of that out, we end up with something close to 8.7 times 10 to the 3 newtons.
Now for part B, we need to find the force sustained by C.T.'s elbow joint. So I'm worried here because we didn't incorporate this force into part A. Is that going to change our answer?
I don't think it really matters, just because the force on the elbow is going to be right at the pivot point. So basically 0 distance. So if it's at 0 distance from that pivot point, that means that we have 0 torque.
Right, okay. So our answer in part A is still the same. But I don't really understand this force in the elbow joint, like what direction it's in or where I should put it.
All right. Well, let me give you a hand with that. Why don't we use this model to figure out what would happen if those two forces were the only things acting on this arm?
Okay, to understand the force in the elbow joint, we can imagine what would happen if we didn't have that force. So Isaac found in part A that the force from the bicep tendon is about 8.7 times larger than the force from the dumbbell. So if you imagine this arm floating in space, and you imagine tying a string to where the bicep connected to the bone, and a string to where the dumbbell was in the hand, and you pull the bicep string with 8.7 times more force than the string from the dumbbell, you would start to see that your arm begins to rotate around the center of mass. But that's not what we're getting here. That's not the motion we want. We want this arm to pivot about the elbow, so we have to have another force that's going to constrain it to pivot about the elbow. And that's the elbow force. So if we want to stop it from rotating clockwise, we need this force from the elbow down onto the bone. So now that we understand the force of the elbow, we can solve this problem. So, like Isaac said, this is a system in equilibrium. Therefore, the sum of the forces has to equal 0. So F tension minus F elbow minus F dumbbell has to equal 0, so that the force of the elbow is simply the force from the tension of the bicep minus the force of the dumbbell. So Isaac found that Ft was 8.7 times 10 to the 3 newtons, and the force of the dumbbell was just mg, which was 102 kilograms times 9.8. But for simplicity's sake, I'm going to approximate that as 10 to the 3 newtons. So that the force of the elbow is 7.7 times 10 to the 3 newtons. Okay, so let's try and put this in perspective. What do you think the average human weighs?
If we had to guess in newtons, I'd say maybe 600.
Okay, so let's see. We have 7.7 times 10 to the 3 newtons, and we'll divide that by 600 newtons per 1 human. Then put that in your calculator, and that's about 12.8 humans. So, in other words, C.T. Fletcher has almost 13 humans worth of weight on his elbow.
That's a lot.
So the real crux of this problem was the force from the elbow joint. And just like the normal force, it's easiest to understand this force if you imagine what would happen if we didn't have it.
All right. Thanks for watching.